All right, so welcome back to Physics with Captain Rod. We are discussing, or about to discuss, the electric potential, but we are starting here by talking about gravitational fields. I kind of want to recap here. So, the cow, young Timmy here in the book. Gravitational force on all of these, I've drawn force vectors for each one and tried to make them relatively proportional to one another. Each one of these is equal to mg. What's differing in these three cases is the value of the mass of each one of these objects. Now, the reason the gravitational force can be calculated this way, whoops, oh boy, stop that. I don't really like Word for this, but the reason that the gravitational force can be calculated this way is because of how the gravitational field is defined. In Newton's theory of gravity, the gravitational field is defined as force per unit mass. At the surface of the Earth, if you take any one of these objects and you measure the gravitational force acting on them, you could do so by putting them on a scale, and then dividing by their known mass, you'll get a value of 9.8 newtons per kilogram. And that value is good, again, pretty well everywhere on the surface of the Earth, two significant figures. If you put these objects somehow, I don't know, maybe on a spaceship or something, and get them up, maybe 20, 30 miles from the surface of the Earth, and you perform the same experiment, somehow measure their weight, divide by the mass, you'll get a smaller value. The gravitational field tends to, or not just tends, but gets smaller and smaller and smaller with distance. And this is kind of the basic fundamentals of Newton's theory of gravity. All right. People are probably wondering, what does that have to do with electricity and magnetism? Well, we're getting to that. So, what I've added now in this picture are what are called gravitational field lines. And what these are, I like to think of them as kind of like the artist version to describe this effect. Here's some rules about field lines. First of all, rule number one. Whatever the vector field is, in this case it's the gravitational field, it's parallel to the field lines at any point. So you'll notice, like right here, actually tangent is probably a better word there, but tangent to the field line would be straight down. Right here, tangent to the field line would be straight down. No matter where I am on one of these field lines, the fields point straight down. Another rule is this: the magnitude of the gravitational field is proportional to the number of field lines per unit volume. Oops. Volume. Meaning that the denser or closer together the field lines are, that represents a stronger field. Now, anybody watching this, what you have to realize is that this is a two-dimensional picture, but you have to realize that there's field lines like coming at you and going away from you as well. I'm trying to represent a three-dimensional thing on a two-dimensional page. So basically, if I were to like pick an area here, some sort of volume, the number of field lines per unit volume describes the field strength. Now, you notice that these lines I drew roughly equal distance apart. That's how you communicate graphically that you have a constant, in this case, gravitational field. And again, I just drew one gravitational field vector where G is defined as force per unit mass with units in newtons per kilogram. Right? Now, we're going to chat a little bit now about potential energy and try to put this stuff kind of together. So here's a picture of a coffee cup. And here's, we'll say, the surface of the Earth or the ground or something. And from Physics 1, hopefully everybody watching this video is familiar with the idea of potential energy. Gravitational potential energy is calculated by mgh. Basically what it is the work that gravity, why did that disappear? The work that gravity will do as this cup moves from, say, here to here. When you describe potential energy, the first thing you typically do is define a datum. I don't know why, but I'm kind of partial to green datums. And with gravity problems, the ground is a very natural place to put a datum. So this coffee cup at this location, right here, we would generally say, okay, that's got a potential energy of 0. Up above the datum, the potential energy is considered to be positive. down below the datum, the potential energy is negative. It's very important to realize that as we move down in this picture, like if this cup were to move lower and lower and lower, it would be decreasing in potential energy. And if the cup is moving up in the picture, it's increasing in potential energy. And if the cup moves to the right, what's happening then to the potential energy?
No change.
Right, no change in potential energy. Very important fact. Now, let me go back to the previous picture. So, I don't know, just draw an object here. It doesn't matter what. So let's say I have some sort of object, doesn't matter what it is. This object, if it moves this way, it's increasing in potential energy. This way will be dropping in potential energy. This way, there's no change in potential energy. Or in other words, we would say that the potential energy is constant. By the way, if I move to the left, the potential energy is constant. And what you have to realize is if it's coming out at you, like towards the reader here, that would be constant potential energy, or away from you. So, very important fundamental to realize about this object. You only change in potential energy when you move parallel to the field lines. Anytime you move with the field lines, you see these field lines have directions, you're dropping in potential energy. Anytime you move against the field line, you're increasing in potential energy. Anytime you move perpendicular to the field line, there's no change in potential energy. Now we're going to go back to our coffee cup here, and we're going to make we're going to play a little algebra trick. I'm going to let this letter, this capital V here, equal GH, and rewrite this equation. And now what it's going to say is potential energy is equal to M times this thing, this capital V here. And if we put the mass on the other side, we get this new term here, this capital V is potential energy per unit mass. What would the units on that be? So what do we, potential energy is measured typically in joules and mass in kilograms. So this is some number that has units of joules per kilogram. And this quantity is calculated by field strength times distance. This quantity right here is called gravitational potential. Not gravitational potential energy. It's related to potential energy, but potential in and of itself is not a potential energy, right? It's what's called a potential. Like its name implies, it's kind of like the ability to have energy. If we think about this coffee cup, yes, it has a potential energy. That's because there's a property in space here called the gravitational potential. And look at how it's calculated. The gravitational potential is equal to G times H. For the sake of this example, I'm going to round gravity to 10. 9.8 Newton per kilogram, that's approximately 10. So this is approximately 10 newtons per kilogram times H. What type of function is this? If V equals 10 times H, if we had to classify that. Times H. If you had to just classify that as a function. It's linear, it's just a linear function. Notice that the potential is increasing with H. Now potential is related to energy, and similarly to potential energy, you can define a zero for it anywhere you want. So this green datum that we're going to define as zero potential energy, we can also define it as zero potential. Now, if the H were 1 meter, then this value would be 10 joules per kilogram. And let's say that this height is 1 meter. Then this point right here, the potential would be 10 joules per kilogram. 1 meter, 10 joules per kilogram. 1 meter, 10 joules per kilogram. I can actually draw a line here where the potential is 10 joules per kilogram. And what that means is if I put 1 kilogram of mass anywhere on this line, its potential energy is 10 joules. Now, I said line, but it's really a surface, because you can move the, let's say the coffee cup left or right, but you could also move it towards you or away from you, and you would be at the same potential. So this is what's called an equipotential surface. My writing is not as good as I would like. Get rid of that. Equipotential surface is just like its name implies. It's a surface of constant potential. Imagine that H were 2. What would our potential be that associates with that? Right, 10 newtons per kilogram times 2 meters. What do we get? 20 joules per kilogram. So if I come up to 2 meters, I can draw another equipotential. Right, this one would be 20 joules per kilogram. And if I come up another 2 meters, this would be 30 joules per kilogram. Now what if we come down here a meter? Can you guess the potential there, a meter down below? Yeah, our potential down here is minus 10 joules per kilogram. So this idea of potential, it's a spatial property. It's a property of space. It describes how much potential energy you can have for any given mass. Okay. Equipotentials are surfaces of constant potential energy. Now look at the gravitational field. The gravitational field points down at all points in space in this picture. You notice a relationship between the equipotential and the gravitational field? What's the angle between the gravitational field vector I drew and that equipotential? 90 degrees. Anytime you move perpendicular to the gravitational field, you're not changing in potential. If you move upstream against the field, so to speak, you're moving towards higher potential. And if you move with the field, you're moving towards lower potential. So if I go back to this picture, I'm going to save this picture as it is. Okay. Okay. If I drew in potential lines, oops, darn it. They'd look something like this. And again, notice that the potentials make a right angle to the field lines. The equipotentials make a right angle to the field lines. So some important things here. First of all, to even have changes in potential, you have to have some sort of field, in this case a gravitational field. If you move with the field, you're dropping in potential. If you move against the field, you're increasing in potential. If you move right angle, then what's happening to the potential? Constant. Potential comes from the concept of potential energy. It's an energy concept. So what do you think? Does that make it a vector or a scalar concept? It's a scalar. Energy concepts are all scalar concepts. Now, the gravitational field is a vector concept, right? It's defined as force per unit mass. Because it's force per unit mass, that makes this a vector type of concept. But gravitational potential is an energy concept. It's defined as potential energy per unit mass, and that makes it an energy concept and hence a scalar concept. All right. Wait, this is kind of slow. Next picture. All right, so in general here, we can think of the gravitational field as force per unit mass. I've drawn a single vector to represent it. That vector I could draw of the same length anywhere on this page because, if you're confined to the surface of the Earth, the gravitational field strength does not vary to 2 or 3 significant figures. I could represent this with what are called field lines. Those would be lines that would be vertical anywhere in the picture, and they would be evenly spaced because the field strength doesn't change. If I have some sort of object, the potential energy of that object is equal to mgh, assuming g is constant. And then another way to describe it is the potential energy is also equal to the mass times the potential, where the potential is equal to the g times h part. So you notice that the potential needs a g, a field strength, and it also needs a distance to calculate differences in potential. This cup, if you move up, you're moving towards higher potential, down, you're moving towards lower potential, left or right, or in or out, there's no change in potential. And again, potential is a property of space. If I pick a point right here, I could calculate a potential at that point. The cup doesn't have to be there because potential is a space property, not a property of the cup. And what the potential allows me to do is, well, if I put the cup here and I know the potential, I would then know its potential energy. So it's just a slightly different way of thinking about potential energy versus how you typically learn about in Physics 1. Moving on. Oh, looks like I, oops. So again, this coffee cup, here's a gravitational field. I could draw a potential at that location. That's what it looked like. There's an equipotential. Oh, looks like I already did those equipotentials down there. So here's a bunch of equipotentials I've drawn. I call them potential 1, 2, 3, 4. A very important fundamental here is to recognize which potentials are bigger than which. So what's the highest potential listed up there? 1, 2, 3, or 4? 1. And then comes potential 2, and then 3, and then 4. All right. What does that have to do with electric fields and charge, huh? Well, I usually like to start talking about gravity because gravity is something that, in second semester physics, everybody should have at least, some experience dealing with gravity. So I usually start by trying to describe potential in terms of something that students are most familiar with. But now we're going to chat about what's called the electric potential and how to calculate differences in electric potential. So electric potential isn't about gravitational fields. Electric potential is about electric fields. So imagine we've got a point in space here where we have some electric fields. Now you notice I drew these field vectors roughly the same length. Right? So that's kind of the math way of saying we're going to assume a uniform electric field in this region. If I drew electric field lines, they would be lines that would run left to right, equally spaced. I'm going to leave them out of the picture, though, for right now. Okay. If I draw a vertical line here, this line would be an equipotential because that line makes a right angle to these electric field vectors. And remember, from the gravity example, if anytime you move at a right angle to the field vector, right, you're moving along an equipotential. You can arbitrarily put a 0 anywhere you want. So in this picture, I called this a 0 potential. Now, why to the right? This is setting it up to be kind of similar to a gravity problem. Normally, you would have your datum here for a gravity problem on the ground, your object up here, the gravitational force is this way, and that force will accelerate that towards the datum if you put your datum on the ground. Well, this particle, the Coulomb force acting on it, meaning the force exerted from this electric field here onto this particle, will be to the right. That's because of how the electric field vector is defined. Remember, the electric field's direction is the force direction on a positive charge. That force is equal to charge times field strength. This is a consequence of how the electric field is defined. Remember that the magnitude of the electric field is defined as force per unit charge. Very quick rearrangement of this, like put the Q on the left, and you get that the force is charge times field strength. Now, notice the analogy here. Remember the gravitational force is mg? Property of the object, property of space it's in. Now look at this. The Coulomb force is charge times the electric field. The charge is a property of this object. The E, the electric field, is a property of the space it's in. See that these equations are very analogous to one another mathematically. The potential energy of this object over here is mgh. Notice that's force times distance. This is the work that gravity does on this object as it moves from here to here. The potential energy of this object right here, if we put the datum here, would be this force times this distance, and I've written that right over here. See how analogous this is to the MGH? Charge, property of the object, E, the electric field in that region, times the distance. Mass, property of the object, G, gravitational field, H times the distance. So the equations of these electrostatic equations we're going to use very, very similar mathematically to the gravitational. They have gravitational counterparts. Okay. Now, where the potential energy is coming from? Well, this is a relationship that's true for all conservative forces. The work done on an object is equal to minus the change in potential energy. The work done on this object, if I release it from here and let it accelerate to here, right? Force times distance equals minus change in potential energy. Now, the potential energy terms can be written PE final minus PE initial, and I can get those potential energy terms from this. All right, notice right here, this is a very important fact. Electric potential is defined as potential energy per unit charge. By the way, what would its units be? Yeah, joule per coulomb. If you rearrange this, you get that potential energy is charge times potential. Whoops. Darn it. This thing's a little tricky to work with. There we are right here, right? Okay. Now, PE final would be charge times potential final, but I have defined the final potential as 0. Minus charge times the initial potential, that's this one. And you'll notice you get charge times potential. This ends up being plus, and the Q's divide out. And we get this expression, that the electric potential is field strength times X. Now, remember what we got before for gravitational potential. It was field strength times H. Right? Field strength times distance. Field strength times distance. What do you think in this picture? Which potential is higher? This one or this one? The one on the left or the right? The left is correct. The left is at higher potential. Now remember from the gravity problems, anytime you move down, you're moving towards what? Lower or higher potential? Lower. And if we move up, higher potential, left or right? No change. Now over here, if we move to the right, what's happening to the potential? Lower, left, what's happening? Higher, up or down? Right? No change. By the way, not just up or down, but in or out of the page as well. These equipotentials are surfaces. They're not just lines. Let me just look ahead here quick and see if nope, I did all right. So now we're going to draw some potentials here. I like colorful potentials. I'm going to use green. Right, so the distance between them is somewhat arbitrary. I'll go ahead and I'll draw another one here. There's another potential. Well, that one got a little goofy, but that's all right. Another one over here. Right, so these are equipotentials. And as we move from left to right, we're moving towards lower potential. Now, let me kind of highlight the really important things here. What is it that the physics person, actually everybody I think, not just physics students, but I think everybody should know what electric potential is. This is what it is right there. That is how it is mathematically defined. It is potential energy per unit charge. So it has units of joules per coulomb. Like most things in physics, electric potential has its own name, or its own little pet unit. 1 joule per coulomb is called 1 volt. Oops, forgot the potential on that. All right, what do we need it for? We use it for energy concepts. Anytime we need a potential energy term, like maybe in the work energy theorem, it's potential energies will equal charge times potential. So again, potential is an energy concept. That means it's not a vector. It doesn't have a direction. And then what do equipotentials look like? They are surfaces. and they always make a right angle to the electric field vectors. And anytime you move with the electric field, you are dropping in potential. Against the electric field, increasing in potential. Right angle to the electric field, no change in potential. How are we doing so far? Questions, concerns, comments about that? I know I've been talking a lot today. I'm going to stop this because this video is probably getting pretty long, and I'll start a new one.